this lecture, we will discover several examples of Hermitian operators. Our first example will be the operator of this kind. We choose some unit vector phi in our state space, and then in the bracket notation we write ket phi and then bra phi. Unlike the scalar product, where bra precedes ket, here we have a reverse order, so it is not a number like in scalar product, but an operator. Let's see how it works. Consider the action of this operator on some vector psi from our state space. If we write the operator and then vector psi, as we usually do when we apply an operator to a vector, we can see this expression is just ket phi multiplied by scalar product of phi and psi. The first thing that immediately follows from this is that when we apply the operator p phi to any vector, we always obtain a vector collinear to phi. The operators of this kind are called the projection operators, since they project the whole space on just one vector. In the matrix representation, such projection operator is a column multiplied by a row, which, as we remember, gives us the square matrix of the operator. Now, if we consider a set of mutually orthogonal unit vectors phi I, then for each vector phi I we can construct a projection pi. The sum of these projections is also a projection. It projects the whole space onto subspace generated by the set phi I. And if the set phi I forms an orthonormal basis in the considered space, then the sum of all projections pi becomes a projection of the space on itself. Thus, it is the identity operator. This relation, which associates the sum of projections to the orthonormal basis and identity, is called the closure relation, and is very useful for the theorem proving, since it allows to substitute identity by the sum of projections at any place of any formula which involves operators. So, what are the solutions of the eigenequation for the projection p phi? First, we may notice that for the vector phi itself, the projection on phi acts as identity. So, phi is an eigenvector with eigenvalue 1. And for any vector which is orthogonal to phi, the projection gives us 0, which means that the second eigenvalue of this operator is 0, and its eigensubspace has the dimensionality of n minus 1, where n is the dimensionality of the whole space. You can easily analyze like this any sum of different projections. The more linearly independent projections you take, the more is the degree of degeneracy of the eigenvalue of 1, and the less is the degree of degeneracy of 0. The identity is also the sum of projections, and it has a single eigenvalue, 1, which is n-degenerate. Now let's consider the operator called X. You can see its matrix on the slide. This operator is very useful and important in quantum computing, since it is a quantum analog of the classical gate NOT. If you apply X to vector 0, you obtain 1, and vice versa. So what are the eigenvalues and eigenvectors of this operator? Well, since it flips 1 and 0, it is quite obvious that it preserves the states which contains both these vectors in the same proportions. The state plus is an eigenvector with eigenvalue 1, and the state minus is an eigenvector with eigenvalue -1. So we can see that x is not just an important operator, it is also a good observable, since it does not have degenerate eigenvalues. X is a matrix 2 by 2, which means that it acts in a two-dimensional space. The two-dimensional space is the state space of one qubit. And the qubit, as we remember, can be represented as a point on the Bloch sphere. So let's see how X acts geometrically on the Bloch sphere. Vectors plus and minus are untouched by its action. Vector 0 comes to 1, and 1 to 0. And the rotational states also flip. 0 plus I1 goes to 0 minus I1, and vice versa. So it looks like the operator x is just the rotation around the x-axis on the angle pi. And it is so indeed. Operator x is the rotation around the axis x. It looks like the name of the operator was not chosen at random. And we have two more axes, y and z. Maybe there are rotation operators for them too? Yes, indeed. Meet the operators y and z. The operator y rotates the space around the y-axis by angle pi, and z rotates the space around the z-axis, also by angle pi. You can guess their eigenvalues and eigenvectors yourselves. Let it be a small exercise. These three matrices, x, y, and z, are called the Pauli matrices, in the name of German theoretical physicist Wolfgang Pauli. They have many wonderful properties, which we will not consider here. The important thing for us to this point is that each Pauli matrix is an observable, with all eigenvalues being non-degenerate. Good. Let's continue. The operator you can see on the slide is called the Hadamard transform, in the name of the French mathematician Jacques Hadamard. And as you can guess, it transforms the 0,1 basis into the Hadamard basis, and vice versa. I literally don't know any algorithm which does not employ this operator. So what about its eigenvalues and eigenvectors? Well, to find this out, you can choose two ways. The first one is to solve a characteristic equation for the eigenvalues and then the system of two linear equations with one unknown parameter. Sounds exciting, but don't hurry to do that, especially since I did not explain what a characteristic equation is, etc. On this picture, you can see the geometrical interpretation of the Hadamard transform action. 0 it maps to plus, and 1 it maps to minus. It is easy to see that both these actions are actually the reflection across this direction painted in red. So the vector collinear to this direction is not modified by the Hadamard transform. This vector has the angle pi divided by 8 with the 0 vector, so we can easily compute its components, cosine pi divided by a and sine pi divided by 8. And its eigenvalue is 1. And we are now experienced enough to expect that the second eigenvector is orthogonal to the first one. Let's choose this one with components sine pi divided by 8 and cosine pi divided by 8. Hadamard transform maps it to itself multiplied by -1. So we can conclude that the second eigenvalue is -1. And no eigenvalues of the Hadamard transform are degenerate. Thus, Adamar transform also represents the complete set of commuting observables.